In this section, we're going to set the proper foundation for the first causal inference technique, randomized experiments. But first, I want to discuss a poem called Road Not Taken by the American poet Robert Frost that is actually pretty relevant to our discussion of Ceteris Paribus as a requirement for doing causal inference. In The Road Not Taken, Robert Frost uses the metaphor of crossroads to describe the causal effect of personal choice and fulfillment. The narrator says that his choice in taking the road less traveled has made all the difference, but in reality we know this to be unprovable. Being only one person, he couldn't actually be sure. Maybe the road more traveled could have made an even bigger difference on the narrator's life. Feeling curious, the narrator may want to revisit the road more traveled at a later date, and compare it to the road less traveled. But this won't work either. The narrator would be older, much wiser, and different in other ways than his old self who had taken the road less traveled by. Then how can we preserve Ceteris Paribus here? The answer is, by varying the treatment variable simultaneously for the same person, and observing both the control and treatment outcome. But this is impossible. Because variation in treatment status cannot be made simultaneously. A person cannot both have taken the road less traveled by, and the road more traveled by. You may be wondering how this situation differs from the plant example, when we talked about controlled experiments. For one, a plant cannot simultaneously be treated with light, and not treated with light. After all, it's not like there is a parallel universe that allows for simultaneity. But we were still able to uphold Ceteris Paribus, because simultaneity is exactly what the controlled experiment emulates. Because we have two groups of plants which are genetically identical, grown under the exact same environments except the treatment status, we are able to observe very accurately what would have happened to the group of plants that had received the light treatment had they not received the light treatment. And how do we observe this exactly? We take a look at the control outcome, the outcome of the plants which had not received the light treatment. The control outcome mimics the counterfactual, what would have happened in the absence of the treatment. In summary, because the two plants that went on their separate roads were identical, comparison of the treatment outcome and control outcome is done Ceteris Paribus, and we are able to confidently say whether the treatment has made all the difference. Mr. Frost, not so much. The United States is one of few wealthy countries that does not provide universal healthcare to all of its residents. But healthcare is expensive, so politicians need a compelling reason to fund it. And one really compelling reason would be a statistically and practically significant causal relationship between health insurance and health outcomes. Our effort to understand the causal connection between health insurance and health outcomes is aided by fleshing out Robert Frost's two roads metaphor. We use the letter Y as shorthand for the outcome variable of interest, health level in this case. To make it clear that we're talking about specific people, we're going to use subscripts as a stand-in for people's unique identifiers like Social Security number. So Y, I, is the health level of individual I. Facing the choice of whether or not a person gets health insurance, person I's health has two outcomes, only one of which is observed and the other is potential. He or she may either get health insurance or not. Remember, a person cannot simultaneously live two lives or travel on two roads, one with health insurance and the other without. But we'll write both outcomes anyways using notation. To distinguish one outcome from the other, we add a second subscript, the treatment outcome, which is the health level with health insurance, is Y1I, for person I, while the control outcome, the health level without health insurance is Y0I, for person I. The unit level causal effect of insurance on health for each person is the difference between Y1I and Y0I. This is interpreted as the causal effect of health level for just the single individual, directly attributable to the variation in health insurance status. Now suppose we have a whole bunch of people, N, in total. There are a total of N people or subjects that we are studying in our sample. For each person in our N-size sample, we have two outcomes, one of which is observed and the other is potential. This is detailed like this. Y11 is the health level of person 1 who is treated with health insurance. Y01 is the health level of person 1 who is not treated and does not have health insurance. Their difference is the unit level causal effect of having health insurance for person 1. And similarly, Y12 is the health level of person 2 who is treated with health insurance. And Y02 is the health level of person 2 who is not treated and does not have health insurance. Their difference is the unit level causal effect of having health insurance for person 2. And we continue the notation this way until we have the unit level causal effect for all N people in our study. Using all of these unit level causal effects, we are going to calculate the average treatment effect of having health insurance. We do this by summing all of the unit-level causal effects and dividing the sum by the number of subjects, which is n. Why do we do this? We do this because we're not very interested in the unit-level causal effect because it's specific to each person. We don't really care if health insurance improves the health of Jane, Bob, or anyone in particular. We really care about the average trend, whether health insurance improves the health outcomes of the general population. The average treatment effect, we denote as lowercase k. Let's visualize what we have been discussing in a table. In this table, there are just 4 units or individuals. We have their y0 and y1, the health outcome with health insurance and the health outcome without health insurance. We take their differences and come up with the unit-level causal effect for each subject. Then we take the sum of the unit-level causal effects, which comes out to be 4. And we divide this number by 4, the number of people in our sample, to get the average treatment effect of 1. This positive number is evidence of a causal relationship between health insurance and health levels. More concretely, there is a positive relationship, meaning getting health insurance improves a person's health by 1, on average, if they didn't already have health insurance, all else equal. But if you can remember our discussion on the impossibility of Robert Frost's metaphor of observing 2 states, treatment outcome and control outcome, we will begin to realize that our data will inevitably look like this, where there is missing data for each subject. Because a person will either be treated or not be treated with health insurance, either y1 or y0 will be missing for each subject. This means that the unit-level causal effect is unsolvable now. And we knew this all along. So what can we do? Well, one way is to estimate the treatment effect by taking the difference of group means, that is, we take the average of the y1 of all those that have insurance, and subtract it by the average of the y0 of all those that don't have insurance. The end result is that we have 1.5 as an estimated average treatment effect. This is clearly not equal to the actual average treatment effect of 1 that we calculated earlier. Let's talk about what happens mathematically when we take the simple difference of each group's outcome means, to see why our estimated average treatment effect of 1.5 deviates from the actual average treatment effect of 1. If you're not familiar with the mathematical notation, that's totally fine. I'll translate the notation into words. So basically, the math is saying that although we're after the average treatment effect involving everyone's y0 and y1, the data we have only contains the y1 for the treated, and the y0 for the untreated, which is exactly what we saw with the holes in our data. This is why we estimated the average treatment effect by taking the average of the y1 of all those that are treated, and subtract it by the average of the y0 of all those that are untreated. This is called taking the simple difference of group means. The math shows us that such a calculation equals the average treatment effect, plus the difference in average y0, between the treatment group and the control group. Remember, this second term, the average y0 for the uninsured, is just the average health level of the people that are uninsured if they didn't have insurance. This value, then, is something we can actually measure. Let's take a look at the first term. This term, the average y0 for the insured, is the average health level of the people that have health insurance, if they didn't have health insurance. And this is something that is unobservable, because these people already have insurance. They've already taken the road of with insurance. So this value is hypothetical in the sense that it cannot be directly measured. So we've just shown mathematically that simple difference of group means is the average treatment effect, plus the difference between 2 terms representing the average y0 of the treatment group and the control group. Social science researchers call this difference selection bias, which means that the 2 groups of people, those with insurance and those without insurance, are not apples-to-apples comparisons. That is, they are not Ceteris Paribus. The insured and uninsured are different in other ways besides just their insurance status. How do we know that the 2 groups of people are different? Well, the people that have insurance are most likely wealthy, educated, employed, and already healthy. And recall that we only want to know the causal effect of insurance on health. Not the causal effect of having insurance, being wealthy, being employed, and being educated, and this is exactly what we are deriving when we compare 2 groups, by taking the difference between their average outcomes. To disentangle the pure insurance effect from the differences in wealth, employment status, and education, among other things, we have to make sure that all other factors are equal, so that the only thing that is different between the insured and the uninsured is insurance status. The important role that Ceteris Paribus plays in deriving a causal relationship should be imprinted pretty securely in our brains by now.